Okay, can everyone see the screen and it's not like messed up? Cool. All right. Hey, everyone. Thanks for having me. My name is Shreyas Vissapraagada, and I am a fourth year now graduate student at Caltech, working with Heather Knutson. And today I want to talk a little bit more about metastable helium, and specifically a survey that we've been doing of metastable helium with the Wide Field Infrared Camera, or WIRC instrument, at Palomar Observatory right here in Southern California. So thanks for the shout out, Jess, in the last talk. So Jess has gone through a great review of all of the awesome stuff that you can do with metastable helium. So I'll try to keep my introduction a bit shorter. But our main motivation here is that planetary atmospheres change over time. This is true in the solar system. You know, to talk about the planet of the day a little bit, we know that hydrodynamic escape likely affected Venus and facilitated the loss of its oceans early in its life. But it's even more true for exoplanets. Due to various detection biases and stuff like that, planets that we detect are often very close to their host stars. They're getting bombarded with high energy radiation, so much so that the upper atmospheres get heated up and can escape. And this isn't just like an academic curiosity, right? It really is a process that has a huge influence on the population of exoplanets that we observe today. So I think that's well captured by this plot from B.J. Fulton et al., where he's showing the frequency of Kepler planets with, detection biases calibrated out as a function of planet size. And you see that between the sizes of Earth and Neptune, we have this bimodal radius distribution. You may have seen this in other talks already. And the interpretation here is really that atmospheric escape is a dominant factor in the evolution of planets. Planets on the sub-Neptune side of this gap are maybe a little bit more massive, and they can hold on to their atmospheres against the influence of atmospheric escape. Whereas the planets on the super-Earth side of this gap maybe aren't so massive, maybe aren't as well suited to hold on to their atmospheres against atmospheric escape. So this process is really, really crucial in understanding the population that we observe of all exoplanets. So given that it's so important, how do we observe it? Well, you might have gotten a hint from Jess's talk, but one way to do so is transit spectroscopy, right? Where we're looking at a planet passing in front of the star and watching it block out some light. So here's a not to scale view of that on its side. And we have some rays of light that, get blocked out by the planet, and some rays of light that can reach our telescope. And that dimming is what we interpret as a transit depth that tells us the planet's size. But in reality, this isn't the whole story. Especially if a planet's atmosphere is escaping, some of those rays of light are being filtered through tenuous, low-density gas in the upper atmosphere. And at any random wavelength, if you were to observe that low-density tenuous gas wouldn't really make a difference. It would be kind of inconsequential. But if you were to choose a wavelength at which that gas becomes opaque, then suddenly the planet begins to absorb much, much more light, and it appears much bigger to us. So if we can find that wavelength that we can observe planets get way, way, way bigger in, then we can infer the ongoing action of atmospheric escape. And so this is exactly what Jess did, and what Jess showed you in the last talk when she studied the size of WASP-107b as a function of wavelength. So this is the spectrum from her 2018 paper. And you see that the spectrum in general is more or less consistent with a clear atmosphere with water, except at 10,830 angstroms, or 1083 nanometers, which is where metastable helium starts to absorb in that upper atmosphere. It starts to become spectrally active. Now, as Jess was saying, due to the resolution of the Hubble Space Telescope, this signal only appears to be like 400, 500 parts per million. But the great thing about that wavelength, 1083 nanometers, is that the Earth's atmosphere is transmissive. And so we can go to a high resolution spectrograph and resolve it in all of its details. And that's what Kirk et al. Did in 2020. Here's the spectrum that they got, showing the excess absorption, so on top of the nominal 2% transit depth, as a function of wavelength. And you see that in the line core, this signal isn't 500 ppm, right? It's huge. It's like 6%, 7%, whereas the nominal depth of the planet is 2%. So when you have planets orbiting bright stars, this technique works great. You can take all those photons and break them up as a function of wavelength, and monitor what that spectrum does over time to make beautiful plots like this. And you can do things like study the velocity profile of the outflow and all that jazz. But the question that we were concerned with was, what happens when you go to fainter stars? Because those error bars on this plot are going to get a lot bigger. And part of the reason that they get so big is because spectrographs aren't perfectly efficient. You know, when you're taking light from the star and breaking it up and sending it through all these complicated optics, you necessarily will be losing light along the way to your detector. So we wanted to think about a way to design an experiment to measure the 10-830 line that doesn't suffer from some of those limitations for faint sources. And so here's what we came up with. We wanted to observe helium photometrically around faint stars. So no longer breaking up the light as a function of wavelength, but just filtering the light and performing transit photometry as you would at any other wavelength from the ground. And our experimental setup is fairly simple. All we do is we take light from the telescope, we put it through something called a beam shaping diffuser, which just helps us mitigate systematic effects. We put it through our ultra narrow bandpass helium filter, and we form the image, and we take many images over time, and we build up our light curve. Now, I'll talk about why the image looks the way it does in a second, because that's really important. But briefly, I want to mention that ultra narrow bandpass here is 0.6 nanometers or 6 angstroms. By comparison, I think the HST resolution element is like 98 angstroms or something like that. So superimposed on the WASP-107 spectrum, here's kind of the region that we're looking at. And so we're averaging over a lot of this structure, right? Which means that our signal is going to be smaller. We're not detecting an 8% signal. We're maybe detecting something that's 1% or less, maybe 0.5%. But if we can make the measurement precisely enough, and thanks to the engineered diffuser we can actually extend this technique down to sources that exceed the magnitude limitations of smaller spectrographs. So to return back to that odd-looking arc-like appearance, this is one of the main considerations that we have to take into account when designing helium observations. So this is the detector that's been uniformly illuminated by a helium arc lamp. So every spot is receiving the same amount of the helium 10-830 line. But you see that only a small part of the detector is sensitive to it. Only a small part is glowing. And that's because the center wavelength of a filter on the detector depends on your angle of incidence through the filter. And for this wide field camera, the angle of incidence changes quite a bit. So we get these radial arcs. But that's okay. We can take this arc lamp flat at the beginning of each night and make sure we place our target somewhere where we're sensitive to helium. So that's what we do in this data set. Our target is up there, the upper left circled in green, and our comparison stars are circled in black. And from here, it's just a question of subtracting out the tellurics. So you can see the OH lines as radial arcs in the sky as well. But because they have such a fixed and unique spatial pattern, we're able to correct them pretty effectively. And then we just do aperture photometry. We count up the photons, we monitor that number over time, and we build up a light curve. And so when we did that, when we commissioned this experiment for one of the planets that Jess mentioned, WASP-69b, here's what we found. At optical wavelengths, this planet, you know, it's a pretty huge planet, so it's been well studied in the optical, and that's kind of what its light curve looks like. It's shallower than 2% to very, very, very good confidence. But our data in the helium bandpass in gray, binned in black, and our best fit model shown in red, reject that optical transit at a confidence of approximately 10 sigma. We detect an excess absorption in the helium bandpass of about 0.5%. And it turns out when we compare this to other observations that have been done with high resolution spectrographs, we get the same answer for how much excess absorption there is, which is a good sign, means that we're not messing anything up too bad with this measurement. So our commissioning observations were successful and got published earlier this year. We can even go a step further. We can infer the mass loss rate and thermosphere temperature of the planet using the models from Antonia Klopčić that Jess described in her talk earlier. So I won't go too much into detail here. All I'll say is, you know, in general, if the mass loss rate were a lot higher, then we'd expect the excess depth that we detect to be a lot larger. And if the mass loss rate was a lot smaller, then we would expect to detect a much smaller signal. And so, albeit with degeneracies, we can use this photometric data set, even though we don't resolve the line shape, to say something interesting and meaningful about the planetary atmosphere. In this case, the atmosphere is escaping at a rate that we inferred of 0.0005 Jupiter masses per gigayear, which means that it's probably not going anywhere. We then took this technique and extended it to other planets. So we turned to WASP-52b, which is a low density planet orbiting a K2 host star of a J magnitude of 10.5, which is beyond what some near-infrared spectrographs can do. And on the left, I show two light curves. The top one has been published, but the bottom one is a new one that we took this summer. And our conclusion here is that if there's a signal, which depending on the data reduction there may or may not be, if it's there, it's much smaller than the signal of WASP-69b. And for various reasons, this is interesting. I will defer until the publication to explicate what those reasons exactly are. But this planet has had other detections of atmospheric species like sodium and H-alpha, another outflow tracer. So there's potentially something interesting going on here. And we have more observations in the pipeline. So this top detection is potentially the faintest system for which metastable helium has been detected thus far. My summer student, Kim Paragas, is the one that's working on it. And the bottom is a detection that I think is quite a surprising non-detection because it looks like a lot of the other planets in our sample, but it doesn't express the same signal. And briefly, as I'm running out of time, if we look at the sample of planets where we've detected metastable helium already, I think the sample already looks quite interesting. On the y-axis, I'm showing a kind of proxy for how big the helium signal is as a function of planetary equilibrium temperature. And weirdly, it looks like planets that are hotter are expressing smaller helium signals, which shouldn't be happening if we think about the physics of atmospheric mass loss. So I think there's something radiatively interesting going on here. With that, I will leave up my summary slides, or my summary, and I will take any questions. Thank you.
Okay, thank you very much for an excellent talk and another aspect of doing these great helium observations. A reminder to folks that please place your questions in the Session 4 Slack channel. I can see some folks typing, but nothing's popped up just yet. So without giving too much away, Shreyas, can you tell us what the new range of stellar magnitudes and transit depths that you think this narrowband photometric approach lets you access? You mentioned that one of your upcoming results is maybe the faintest star that's been done this way?
Yeah, totally. So magnitudes I can totally say. I think I initially thought we could get down to like J of 10.5 and that'd be it. But the new precisions that we're getting is, you know, if a planet had a WASP 107 like outflow, we could get down to, I think, J of 12.
Okay, very cool. Taking questions from the chat now from Jason Wang. Is getting reference stars into the helium sensitive annulus an issue? Can you rotate the field of view of the detector?
Great question. We can't rotate the field. Our assumption is that the variations that other stars experience are the same throughout the detector, even though they're on different parts. We're looking at different parts of their spectrum. And you're right to sort of question that, but we haven't seen any evidence empirically that that's a bad assumption, looking at things like variability in comparison stars, for instance, that are on the helium line versus off. So currently we can't rotate the field or anything like that, so we can't make that measurement.
Gotcha. Okay, and in your final minute of questions, question both from Jess Spake and Akash Gupta, both asking, do you have an idea for what physically is causing that downwards trend in the last plot that you showed?
Yeah, I think I have a couple of ideas. I have no idea if any of them are like anywhere close to correct. I think there has to be something radiative going on, which means either that assumption of isothermality in the atmosphere for the outflow is violated for some of the hotter planets in the sample, or because they're so close to their host stars, we have some fraction of helium that's going predominantly into the ionized state rather than staying in the neutral state. And this is something that Antonia Klopčić has looked at as well. Although I think when we chatted about it, she mentioned that those stars were typically closer in than the ones in our sample. So I think the question is still very much open.
Very good. Okay, well, we are just about at the end, so I'm going to call that good to keep us on time, but thank you again for an excellent talk.
Thanks.
And now we will move on